Hello, everyone. My name is Joe DeMartini. I'm a PhD student at the University of Maryland, College Park, working with Professor Derek Richardson. Today, I'm going to talk to you about the influence of irregular grain shape on the Brazil nut effect in low gravity. This work was supported by the GEODES survey mission. So first, a little bit of introduction. The recent missions to asteroids Bennu and Ryugu by OSIRIS-REx and Hayabusa-2, respectively, have shown that rubble pile surfaces can be highly complex, with such features as smooth versus more rough patches of terrain, indicating a large variability in the surface grain size distribution, as well as large boulders without associated craters, indicating possible vertical regolith migration. Both missions also measured approximately 50% bulk porosity on these asteroids. That is a 50% under density relative to if they were monolithic. And so one possible explanation for these large surface boulders I've singled out here without associated craters could be the Brazil nut effect. What I want you to imagine for the Brazil nut effect is that I've got a big jar of mixed nuts. And for argument's sake, all of them are equal density. The Brazil nuts and everything are sort of spread out throughout originally. And if I shake it up really hard, really vigorously, then after some time, the Brazil nuts, the largest particles, will rise to the top. This is true. We have shown this to be true in granular media, sort of in general. And the mechanism at work here is sort of what's called void filling, where shaking this up, the larger grains create these voids that the smaller grains sort of fill into, and it propagates up and up and up through the medium. And so one question that we aim to answer here is whether high porosity granular media create a more efficient Brazil nut effect. Higher porosity, more void space, possibly more efficient rise of larger intruders. And the way that we're going to investigate this is numerically. We use the parallel n-body gravity tree code PKD-grav, which uses a soft sphere discrete element method to model contacts between spherical particles, allowing for very slight interpenetration of the spheres at the point of contact as a proxy for surface deformation, and with the degree of interpenetration mediated by a restoring spring force. This approach also allows us to model rolling and twisting, as well as sliding friction, and normal and tangential restitution between our spherical particles. Recently in PKD-grav, we have gained the ability to efficiently simulate large numbers of irregularly shaped particles using what we call aggregates. Essentially, we glue together a couple of spheres into an irregular shape. And this is great because suddenly we gain the benefit of being able to model shape effects in a granular medium, but we maintain the relatively simple calculations for spherical gravity and sphere-sphere interactions. And the importance of being able to simulate with aggregate particles has to do with the porosity of granular media. I mentioned before, Ryugu and Bennu were measured to have approximately 50% bulk porosity. And the most efficient packing distribution for monodispersed spheres is the hexagonal close pack, which you can see in this image up here from my 2019 paper. And this has about a 26% porosity in a medium of monodispersed spheres. We can then move to a slightly less efficient packing distribution. We have a random packing of spheres that are all different sizes, and we get somewhere around 50% porosity. And you can see that here in one of our collaborators' recent publications. But when we make a medium of mixed aggregate particles, irregular shapes, we've found that we can get up to 70 or even 80% porosity in the medium. And this is great because in the OSIRIS-REx tag sample return in situ experiment, the tag arm penetrated like a half a meter deep, like a half a meter deep into the regolith layer, indicating potentially very high porosity, much higher than the 50% bulk porosity number. And this is reasonable because you can imagine at the surface, there would be a lot less overburden pressure than deeper down in the asteroid. So on to our actual experiments here. This is the way that we set up our simulations. We have a sort of periodic box. We have periodic boundaries. And we have a large red Brazil nut aggregate down at the bottom here, which is approximately the same density as the medium around it. We then drop these aggregate particles down around it so that they can pack sort of randomly around the Brazil nut. And we do this for all 5 of the aggregate shapes that you see up here, as well as with single spheres for comparison. And we do analogous simulations turning such toggles as interparticle friction, which has been shown to be an important factor in the rise speed of the Brazil nut particle, interparticle cohesion, Brazil nut size ratio, the ratio of the Brazil nut to the size of a typical particle in the medium, as well as the strength and style of the shaking of the medium. So let me exemplify this with one of our earliest simulations here, where basically we have this box full of particles, and you'll see the Brazil nut come up in just a second. It's the only red particle in the simulation here. And we basically give all of the walls a sinusoidal oscillation with amplitude and frequency chosen such that the equivalent acceleration is 3 times that of the ambient gravitational acceleration. This is a Froude number of 3, as it were. And we measure the height of the Brazil nut as a function of the number of oscillations. So this red dashed trace that you're seeing here is the Brazil nut height during the simulation. The blue dashed trace is the median height of a particle that is not the Brazil nut in the particle bed. And this black dashed line indicates the initial height of the particle bed. So when the Brazil nut reaches approximately this black dashed line, it has reached the top of the medium. Our more recent experiments, as I showed before, have been using periodic boundary conditions. These are ongoing, but you can tell just from this figure in comparison to the last one that it's a little bit more difficult to interpret the results. I believe if we simulate this for just a little bit longer, that the Brazil nut comes up to the top and sticks there. So this is the work that is ongoing. In addition, we have a different method of shaking. So rather than just those sinusoidal oscillations on the walls, we can use acceleration data from a seismometer about 150 kilometers from one of the artificial impacts on the Apollo 16 mission. And we can scale the magnitude of that acceleration to simulate being closer or further from the impact site. And so you can see here, we sort of do repeated shakes with different magnitude accelerations to say, oh, we're much closer this time, further this time. I'm starting to run out of time, so I'll go to my conclusions here. One of our main findings is that systems of irregularly shaped grains produce much more porous media than systems of discrete spheres. And to that effect, we find that simulating shape is very important for accurately modeling the Brazil nut effect. Here is just a quick grid of our initial results for some of these simulations with irregularly shaped spheres, particles in the Brazil nut effect. And we find that in most cases, the Brazil nut rises to a taller relative height and more quickly than in simulations with only spheres. We are also in the future working on simulating the sound speed of through granular media with impact experiments compared to similar laboratory experiments. I think I'm out of time here, so thank you very much and happy to answer any questions.
Great, thank you so much. And modeling granular media is near and dear to my own heart, so it's always nice to see. So yeah, as usual, feel free to use the chat box if you have any questions. I think I see a hand raised by Antara, if you'd like to unmute.
Sure. This is actually really interesting, and it's relevant to something we're studying right now. So I had a question. So on Bennu, we're seeing this dichotomy of boulders with different densities and as well as different porosities. So given the results that you're seeing right now, which look quite promising, do you have any predictions for what the implications of different densities might be?
Yeah, so for the Brazil nut effect, for the most part, we find actually that density is not a huge factor. It's possible that when your large particles are significantly underdense compared to the particles in the medium, that you actually get what's called the reverse Brazil nut effect, where the larger particles actually move down lower, which is sort of the opposite of what you would think in terms of like buoyancy rules, right? The less dense things should rise, the more dense things should drop. But there's a lot more work to be done about that. But the different densities, that's really interesting. And depending on, you know, the proportions of different density material on the surface, that could, yeah, that could be interesting to look at. Sorry, I don't have a better answer for you.